Good afternoon, Rich Nass, Embedded Computing Design, here for another in a series of 8 videos that PICMG is hosting with Embedded Computing Design to help launch the COM-HPC standard. Each of the 8 videos looks at a different aspect of the standard. Some are higher level, some are getting a little bit into the nitty gritty. This particular one falls into that latter category where we're going to get a little bit into the weeds. This one is named Delivering the Bleeding Edge Power and Performance, and it's an overview of the signal integrity and power integrity of COM-HPC. And to do this, I have Burrell Best of Samtec. He is an industry standards manager at Samtec. He's also the chair of the Signal Integrity Subcommittee at PICMG. Hello, Burrell. How are you?
I'm doing well, Rich. How are you today?
Very good, thank you. So did I describe that right? I don't mean to say you're going to get down into the weeds or anything like that, because I know we have to keep this fairly high level. Right. And this is a primer for people, but what exactly are you going to be talking about in this presentation?
So we'll go through some of the initial requirements for the connector that we chose for COM-HPC. We'll go through how we determined the number of power pins that we needed, and then we'll go through the SI and PI, or signal integrity, power integrity subcommittee, that helped to define the channel recommendations for the high-speed channels that will be used on a COM-HPC system, and all of that is documented in the specification.
Okay, let's do it.
Okay, the title of the presentation today is Delivering Bleeding Edge Power and Performance, an overview of the SI-PI subgroup activities enabling COM-HPC. So this presentation will cover some of the high-level targets that we started out with for COM-HPC. We'll go through the connector features of the connector that was chosen. We'll go through power delivery and determining how we were able to determine the number of power pins that we were going to need for a COM-HPC system. We'll go through the SI subgroup structure and some of the ownership responsibilities that each member company in the subgroup had, and then we'll go through some of the subgroup tasks. So the modeling that we used, will show a frequency plot of the connector that we're using. We'll go through the channel topologies, how we did the channels, PCB stack up, and then in the end we'll do a PCI Express budget example, which was one of the many channels that we did that will be documented in the COM-HPC revision 1.0 specification. Okay, so the high-level targets for COM-HPC. One of the first things that we were requested to provide was a high pin count. So COM-HPC will be an extension of COM-Express. And one of the biggest improvements or extensions of that are the amount of I/O that will be in a COM-HPC system. The other thing was PCIe Gen 5 compatibility. So that's a 32 gigabit NRZ signal, and it's a very demanding channel. And then also 25 gigabit Ethernet. The other requirements were a 5mm and a 10mm mated connector. And the wattage here is around 360. It originally started at about 200 watts and slowly creeped up to where it is today. And we'll go through that in the slides to come. On the right-hand side there, you see the connector that was chosen for COM-HPC. The first connector, the 209946-01, is the module receptacle. So that'll be on the modules. The next in line to the right in the center is the 214802, and it will be the 5mm mated set with the receptacle, and then the one furthest to the right would be your 10mm mated stack. So the color is natural. That will be the connector in the COM-HPC system. So if we look at COM-HPC as an extension to COM-Express, and we hypothetically wired up the connector in a ground signal ground wiring pattern, and we use the highest performing channel that the connector is rated for, we can get some metrics here as a comparison. And what you come out or come away with is that the COM-HPC connector is a 4 times improvement over COM-Express. And if you were to take a Gen 5 channel, which is 32 gigabits, and wired it up in the channel that I suggested, you can get a 4096 MAC aggregate data rate. And another way to look at it is just in the footprint itself, which gives you 2088 gigabits per inch squared. COM-Express is similar, but it's rated for Gen 3. I do believe there's a Gen 4 connector that's becoming available. But as you can see, just from the very beginning of the project, this was the improvement that we were looking to make. The COM-HPC connector is an open, flexible pin field, or flexible open pin field here. And what that means is all the pins are the same. It's an array connector. You can define differential pairs, signal-ended signals, and power, however that fits your application. In our case, all the pins will be accounted for, but just to show you, starting out, when we were just trying to find the number of pins that we needed and pin assignments, you can see that using the open pin field has its advantages. Another feature of the COM-HPC connector is the BGA solder ball attach, and that eases solder reflow to the PCB. The other is the 1 millimeter contact wipe, which is edge rate contact design that Samtec has, and it provides a very good connection between the receptacle and the plug. Another feature for the COM-HPC connector, and was one that came from some recommendations from some of the member companies early on in the project, was we found that increasing the row-to-row spacing had a lot of advantages for this application. One of the things that we wanted to do, and I jumped ahead here, is we wanted to maintain the ground signal ground density. And to do that, we actually increased the middle row, and what you see on the right-hand side here is only 3 rows of a 4-row connector. The center row was separated by 2.4 millimeters, and the outer row was 2.2 millimeters. And just this little bit of spacing actually helps to mitigate crosstalk, but it also allows for more ground vias, which also does the same. And so it reduces crosstalk quite a bit and allows us to get the 32 gigabit performance that we were seeking. And it also eases just routing out of the connector pin field. So routing vertically or horizontally is much easier with the way we space the rows out. And that was actually requested by the member companies early on. So power delivery, we'll get into that. So the first order of business in the project was determining how many power pins that we needed to power a module. So obviously the number of pins are limited, and you want to reserve only what you need. And the IO pins are really the differentiator in the COM-HPC system. So they're very precious. And so you want to have as many IO as you can have. So the first thing we needed to do was look at the power budget. Like I said before, the power budget started out somewhere around 200 watts, but it increased as we realized after some testing how much margin we had in the connector itself. Right here are 2 budgets, power budgets that will be in the specification. The one on the left is for the server class module, and the one on the right is for the embedded client. As you can see, the CPU total design power, it ranges. A server class goes from 35 to 150 watts. The client goes from 25 to 95 watts, and that may be variable. These aren't exact limits. And then the DDR4. So you can have up to 8 DIMM sticks in a server class, and up to 4 in the embedded client. And just starting, we'll start with the server class budget here. So the actual component would be on the left-hand column. You have your CPU, your PCH chipset. You've got your memory, and then some miscellaneous power. and spare power, and then the power efficiency of the actual power delivery system. And each one of those components in the table has a budget associated with it. As you can see at the bottom there, the server total budget comes out to 358 watts, and the client total budget is 251 watts, which is quite impressive. Okay, so to get to the number of power pins that we needed, we had to do a lot of testing. And basically, we designed some boards. We did 3 iterations of the test. This is the final footprint that we ended up on. You can see on the left-hand side, the module PCB, we used an 8-layer board. We used 1 ounce copper. And then the carrier PCB was 6 layers. One of the things that we did to help dissipate the heat, or to spread the heat out from the connector, was we flooded the plane around the connector where the power would be delivered. And as you can see on the left-hand or on the right-hand side, you have a graphic of the footprint, and then you actually have a picture of the connector being tested. And what those 2 wires are thermocouples that actually measure the heat that's generated when we do a current carrying capability test. And it's a measure of a 30 degrees temperature rise. And the results of the test, and what we have here is a 20% derated value. So that's 80% of the value, the 1.12 amps per pin. And then a COM-HPC system will have 28 power pins to deliver the required power to the modules. And that satisfies our needs. So right here is the COM-HPC input power tables, and these will be in the specification. As you can see, the most important value there is your VCC. And if you start on the power rail there on the left-hand side, and then you work your way to the right, you can see the different values in the table. You have the 5-volt standby, and then the VCC RTC is your battery power. And what you can see here halfway through the table, the max module input power is 358 watts. And then the bottom table is a representation of the client module, and it maxes out at 251 watts. All right, we'll go into SI performance. So the objective of the COM-HPC SI subgroup was to determine loss budgets for the high-speed interfaces. And so a small subset of member companies divided or merged from or diverged from the main group and did this work in parallel. Samtec chaired the group, so Jim Nadolny originally chaired the group and then handed it off to me. And then Stefan Milner was the editor from Contron. And so he took all the data that we produced and drafted into the specification. So the work group, we built and shared model collateral to ensure consistency. So we built models, 3D models using HFSS for the module and carrier PCB models, the connector models, and then the traces, the strip lines that would connect the different components in the channel, which we'll go through in a moment. We built and simulated channel topologies, and then the results, as I said, were documented in loss budget tables that will be in the specification. Okay, so here's the structure of the group. So three main companies took ownership of the interfaces. So AdLink took Ethernet, Samtec took PCI Express and USB, and then Intel took SATA and DDI, which would be HDMI and DisplayPort. And then Contron took the results and put them in the specification. So it was a team effort. We shared models, like I said. And let's see, AdLink, Armin Jacques was the lead there. Samtec was myself and Jim Nadolny, and then Ben Silva with Intel did all of the simulation work in the subcommittee. So here's some examples of the 3D models. And like I said, they were built and solved using ANSYS HFSS to create S-parameter models. And these models were shared amongst all the member companies so that we simulated the exact same components in the channels. So just starting from left to right, there's a COM-HPC 5mm connector model, 10mm connector model. And then we also had to model the module and carrier PCBs. And then there were other components, various components in the channels that there's differential vias and strip line models that we all shared. This right here is an example of the connector only insertion loss. And what you can see is it's very, if you're familiar with and reading insertion loss, it's a very good measurement of the connector and is well above the PCI Express 32 gigabit limits that were required. Return loss too was very good, well under probably 15 dB out to well out to 25 gigabits or gigahertz. All right, so the channel components. S parameter models were concatenated using tools such as MATLAB to build the full channels. Simulation tools such as CSIM and COM simulated the fully assembled channels. And both of those tools are publicly available tools. CSIM is one that was adopted by PCI-SIG. It's a research and development tool. And then COM is actually defined in the IEEE specifications, and it stands for channel operating margin. Component losses are listed in budget tables included in the COM-HPC specification. So if you took this example channel here and you started in the left-hand corner at the transmitter package, then each individual component in the channel would add a loss to the channel to build a full channel. And so just going from left to right, you'd have a package, strip line to vias, a coupling capacitor to another via to a strip line, and then to the COM-HPC connector. So there'd be a module breakout region and a carrier breakout region, a strip line, and then a receiving package. And so that would create a full channel. And in this example, this would be a PCI Express channel, and one we would be a device down topology, which we'll go over in just a moment. So the two main channel topologies, which were inherited from COM Express, are what you see here on the screen. So we have a device down, and then we have a device up. So there's a representation of what that channel would look like, the physical channel would look like. So on the device down, you have a module, CPU module, and then the yellow lines in the green rectangles there are the strip lines that go to a coupling cap. That would traverse a COM-HPC connector to the carrier board and to a device down on the carrier board. The device up would have two connectors in the channel. Again, you would travel from left to right. In this example, CPU module would go through the COM-HPC connector to another slot connector or edge card connector to a device on a plug-in card. And those were the two primary topologies that we simulated in the SI subcommittee. Okay, so this is a budget example. So this is what it actually got populated in the specification. So in this case, it's a PCI Express device down insertion loss budget. And all the loss elements, excuse me, are in the left-hand column. And then each generation of PCI Express assigns a budget limit to the different elements. So you have a module package, excuse me, module routing, coupling cap and vias, the COM-HPC connector, carrier routing, and carrier package. So in each case, as the frequency increases between Gen 3 and Gen 5, those loss elements increase. And so we have a table here that actually is a good rule of thumb for system designers that are building these channels to kind of understand what the limits are and what the budgets that we would anticipate in this type of channel. And then going further, in each one of the examples, we use different loss PCB materials. And based on the losses, so a standard loss, a mid loss, a low loss, or very low loss material, and as you go from left to right, the material gets better. And so your channel lengths would increase. So they exhibit less loss as the material gets better. And this also would be included in each one of the interfaces that we simulated, which would be Ethernet, PCI Express, USB, etc. And that concludes the presentation today. Again, I'm Burrell Best. I'm Samtec Industry Standards Manager, and I was the chairman of the SI subcommittee. And that's it.
Thank you, Burrell. One question for you, if I might. Was there discussion about using the same connector from COM-Express so it would really be a one-for-one replacement, or was that not feasible?
So it wasn't feasible for two reasons. One reason was just the performance of the connector. The initial requirement was to be able to support PCI Express Gen 5, which is a 32 gigabit interface. So that was one reason. And then the other reason is they wanted to expand the number of IO ports. So PCI Express, Ethernet, etc. And so for those two reasons, they chose a different connector. And the COM-HPC connector that we developed was that connector.
Excellent. Well, thank you very much. That was Burrell Best, as he just told you, from Samtec. And this is one of 8 videos that all explain a different part of the brand new COM-HPC standard from PICMG. So check them all out.